Okay, thanks. So yeah, thanks everyone for joining today's AI seminar again. Today I'm happy to host Hangfeng's talk. He's actually a final year PhD student working with Professor Dan Ross and also Weijie Su at UPenn. So his research interests mainly focus on machine learning and natural language processing, a little bit of machine learning theory as well, from what I know. And with a focus on moving beyond scale-driven learning. So specifically, he works on incidental supervision for natural language processing, the interpretability of deep learning, deep neural networks, and also reasoning in natural language understanding. So I invite him today to give this talk about incidental supervision for natural language understanding, because I think this is really a very important frontier research direction people are talking about these days. So yeah, let's welcome Hangfeng to just give his talk about his research in this area. Yeah.
Okay, maybe I can share my screen. Okay. Hi everyone, I'm Hangfeng, a fifth year PhD student at Penn. First, I want to thank Wu Hao for his invitation and introduction, thank Peter and others for technical support, and thank everyone for coming to my presentation. Today, I'm going to talk about incidental supervision for natural language understanding. Nowadays, we tend to use a lot of online software in our daily life. For instance, as PhD students, we usually use Google Scholar, Wikipedia to search relevant knowledge. And at the same time, we often play with Twitter, Facebook, and Reddit to connect with others. We can see that these behaviors involve a lot of natural language. And some information cannot be easily expressed by other modalities. Therefore, natural language understanding is everywhere and almost unavoidable. We need to move further in this direction. However, there are a lot of difficulties in this direction. For instance, the complex mapping between the meaning space and the language space. As we can see, we can use multiple natural language expressions to express the same meaning, which is known as variability. At the same time, ambiguity means that one natural language expression can have multiple meanings. For instance, if we want to determine if Jim Carpenter worked for the government, we can simply say that Jim Carpenter worked for the US government, but we can actually use other expressions to indicate the same meaning. For instance, the second last one, Russian Interior Minister Yevgeny Topolov met yesterday with his US counterpart, Jim Carpenter. In this sentence, we don't really talk about something about job or work, but we still know that Jim Carpenter worked for the government. This process requires complex competence reasoning. On the other hand, let's look at the two sentences about Chicago. We can see that Chicago here can be referred to a font, an album, or a band. None of them are referred to the most popular meaning, Chicago city. So we can see that even for a small term, we can have multiple meanings. In a word, the mapping between the meaning space and the language space can be quite complex. Furthermore, the structure of natural language itself is also quite complex. For instance, given the sentence Hangfeng is presenting his work, we can have quite a complex hierarchy from character to words, to phrases, to sentences, and to paragraphs and documents. On the other hand, we can view the sentence from different perspectives, such as topic, sentiment, stance, style, complexity, and others. In a word, the structure of natural language can be quite complex, involving complex hierarchy and perspectives. Given that the tasks in NLU are quite complex, how could we supervise them? A standard machine learning methodology is as follows. Given a task, we try to collect data for the task and annotate it. After that, we simply learn a model for that, usually deep networks here, and we don't really know why it works. However, we will never have enough annotated data for all the tasks we need. First, we don't even know what are all the tasks, because natural language understanding involves multiple domains, multiple languages, and multiple perspectives. The most disappointing thing is that we usually end up learning a dataset instead of learning the task, because every dataset has a strong bias on the task, and we don't really know how to estimate the population risk for the task. Therefore, learning is more like training on many examples based on the strong memorization ability of deep networks. In a word, current methodology is not scalable and more often makes no sense because annotation for complex tasks can be quite difficult. For instance, given a quite simple sentence, where is hard to say. To annotate the constituency passing tree, we can see that the annotation is quite complex and requires expert annotators. To elevate the supervision bottleneck in NLU, a promising way is to use natural language to annotate natural language. This idea is from question-answer driven semantic reliability, QASRL, and question-answer meaning representation, QAMR. The key idea there is to use QA pairs to represent the predicate argument structure of a sentence. For instance, given a sentence, P. Area Lincoln, 61 years old, will join the board as a non-executive director November 29. Given the first question, who will join as non-executive director, the answer is P. Area Lincoln. We can see that this QA pairs indicates that P. Area Lincoln is the A0 or agent for the verb join. Similarly, we can use other QA pairs to indicate similar predicate argument structures in the sentence. Another way is to make use of other types of supervision signals. For instance, given the task of name entity recognition, we can actually use lots of types of signals. For instance, we can directly use the gold signals for NER annotations. We can use unlabeled signals, partial signals, noisy signals, cross-task signals, constraints, cross-domain or cross-lingual signals. As a recap, so in standard machine learning, given a task, we will try to annotate the data, and after that, we will learn the model. For different tasks, we will do the same thing multiple times. This methodology is definitely not scalable. Therefore, Dan proposed the incidental supervision to move beyond supervised learning. The key idea for incidental supervision is to use additional signals, not simply directly use annotations for some specific tasks. These incidental signals can include unlabeled texts, constraints, prior knowledge, and others. In this direction, we will try to understand, acquire, and use signals that were not put there to help a specific target task. In this topic, we focus on improving NLU by exploiting incidental supervision signals in the following three directions. First, we will try to exploit information from some cheap signals to help various tasks. Second, given a specific target task, we will try to select appropriate signals in a wide range of incidental signals. Third, we will try to design efficient algorithms with both theoretical guarantees and empirical evidence to exploit specific types of incidental signals, especially signals that are hard to use. The key takeaway for this talk is that incidental supervision is beneficial for natural language understanding, and the better understanding of natural language properties can be more helpful. The relevant publications are as following. In this talk, I will mainly focus on the top 3 papers. Now let's look at the first part, incidental supervision from QA signals. Given a sentence, the soldier harmed to Jim's sister Joyce as she walked to town. Traditional semantic representations such as abstract meaning representation AMR will have quite complex annotation for the sentence semantics. Fortunately, QAMR use QA pairs to represent the similar predicate argument structures. For instance, the first question, who harmed to Joyce? The answer is the soldier. This QA pair indicates that the soldier is the A0 or agent for the harm. The most interesting question is the last one, who is Joyce's brother? And the answer is Jim. In the sentence, we simply say that Jim's sister Joyce, but in QA pairs, we can also know the reverse relation, which is not covered by traditional frameworks. The takeaway here is that AMR annotations are expensive, require expertise, have limited expressivity, and are not scalable, while QAMR annotations can be done by non-experts and convey more information. A natural question here will be, can we use low-cost signals such as QA data to help tasks that require this semantic information? In this part, we focus on providing an improved sentence encoding based on the QA data to help other tasks. A naive way is to further pre-train BERT on the QA data. However, when we compare BERT for the pre-training on QAMR and the BERT itself, we found that further pre-training on QAMR can be helpful for paired sentence tasks, but can be harmful for single sentence tasks. The takeaway here is that simply for the pre-training BERT is not enough. Why? Because we need to rethink about sentence encodings or sentence representations. There are at least two types of sentence encodings here. First, standard sentence encoding. Given a sentence, we want to encode everything about the sentence. For example, standard sentence embedding such as skip source belong to this type of sentence encoding. But actually, we also have conditional sentence encoding. Given a sentence, we don't need to care about all the information in the sentence. We only need to care about the information relevant to some attention. For example, in the machine reading comprehension, given a question and a paragraph, in order to answer the question, we don't need to know every information in the paragraph. We only need to know the information relevant to the question. In a perfect world, standard sentence encoding, including everything, definitely include conditional sentence encodings. But in practice, there's a trade-off, because if we want to get more pieces of information, we definitely have a lower quality. Therefore, there's a trade-off between the quality and the quantity of sentence semantics that a model can encode. Based on the two types of sentence encodings, we propose QUIZ, question-answer-driven sentence encoding. There are two implementations of QUIZ. The first one is SQuiz for single sentence tasks, such as semantic labeling. For every sentence, we will try to include as much as information as possible. For instance, in semantic defensive parsing, we will try to know the semantic relations in the sentence. In this way, we will distract the interaction from the question to the sentence. Why? Because if we directly extract the sentence representations based on the sentence and then probe the sentence embeddings will multiple questions. If the sentence encoding can support various types of questions, then it means that the sentence encoding convey a lot of information. That's the ideal goal for the standard sentence encoding. In practice, we simply use the paths in the black box to extract features and concatenate them to word embeddings for downstream tasks. Another implementation of QUIZ is pQuiz for paired sentence tasks such as text entailment. For instance, given a premise, two main Pascal's competing near-rise, to know whether a hypothesis can be entailed or not, such as people are riding bikes, we only need to know the information in the hypothesis that are relevant to premise. In this way, we directly use BERT for the pre-training on QA as pQuiz. Why? Because QA task itself is a paired sentence task. And when you train the model on QA, we already know how to get attention from question. So in practice, we simply concatenate the paths in the black box with BERT and then fine-tune them in downstream tasks. We compare SQuiz and pQuiz on several tasks and found that SQuiz is better than pQuiz on single sentence tasks, while pQuiz is better than SQuiz on paired sentence tasks. The results indicate that it's necessary for us to distinguish two types of sentence representations, and this distinguish can help us to design better models. Finally, we evaluated QUIZ on 5 single sentence tasks and 2 paired sentence tasks in both low resource setting and full setting. We found that QUIZ outperforms BERT on both single sentence tasks and paired sentence tasks, especially in the low resource setting. The results indicate that QUIZ can provide extra features compared to BERT. Okay. Now let's look at the second part, quantifying the value of incidental signals. The key for incidental supervision is to use incidental signals x tilde y tilde instead of supervised signals x y. Based on the terminology in transfer learning, we use inductive incidental signals to denote the signals with quite different labels, namely y tilde compared to y, such as partial labels and noisy labels. Similarly, we use transductive incidental signals to denote the signals with quite different inputs, namely x tilde compared to x, such as cross-domain signals or cross-lingual signals. Finally, we also consider mixed types of incidental signals, such as a compilation of partial and noisy signals. A natural question here is that, can we provide a unified framework for incidental signals and quantify the extent to which various incidental signals can help the target task? Now let's take a look at the concept class for some intuition. Given the big C for the concept class, and for every concept small c mapping from input x to output y, learning theory always shows that the size of the concept class determines the incidence of the learning problem. As shown in the transition bound, we can see that law in C plays an important role there. Smaller size of the concept class would lead to smaller transition bound. Therefore, we propose to use incidental signals to reduce the size of the concept class. And the relative reduction on the concept class can serve as an informativeness measure for the informativeness of incidental signals. Specifically, given the original concept class C, we can use incidental signals to reduce the concept class to a smaller one, C tilde, and the relative reduction on the size of concept class can serve as an informativeness measure. Specifically, let's look at a structure prediction problem where X has two binary variables and Y also has two binary variables. If we know nothing about the concept class, we actually, for every input, we will have four choices of outputs. But what if we know some partial data? Even though we don't know the exact label for input 0, 0, but we know the first label for 0, 0 is 0, and the second label for 1 is 1. In this way, we can still filter out some unreasonable concepts. For instance, we know that we cannot map the input 0, 0 to the label 1, 0 or 1, 1. In this way, the concept class can be reduced in a smaller one, and the size is 64. So in a word, in PAC setting, we use incidental signals to reduce the concept class to a smaller one, and the relative reduction of the concept class can serve as an informativeness measure. Now we can consider more practical cases where concept class will be associated with some probability measures. In this way, we are known as PAC-Bayesian setting. We will use incidental signals to impose the prior. Why? Because the key term in transition bound for PAC-Bayesian setting is the KL divergence between the prior and the posterior. If we don't know any information, the prior definitely be uniform. But if we know some extra information, we can use incidental signals to estimate a better prior to make it closer to the posterior. In this way, the KL divergence between the prior and the posterior can be reduced. And this reduction on the KL divergence can serve as an informative measure, which is called S prime. It's also our proposal, PABI, a unified PAC-Bayesian informative measure. In practice, we also approximate PABI with an entropy-based informative measure S prime height. So the good news for PABI and its approximation is that they can handle infinite concept class and can handle probabilistic cases. A good thing is that for non-probabilistic cases, the three informative measures are equivalent. This equivalence not only indicates that the approximation of PABI is good, but also indicates the consistency between informative measures in PAC setting and PAC-Bayesian setting. In practice, we simply use the approximation of PABI as prime height in our experiments. Now let's look at some simple experiments. We consider a main task named entity recognition, and on the outloads a simple model, two-layer neural networks with 5 gram features, and the algorithm is bootstrapping with incidental signals. We will first use gold signals to initialize the model. After that, we will use an EM algorithm to bootstrap on the large scale unlabeled text for incidental signals. Note that in EM algorithm, we need to assign some procedural labels on unlabeled texts, and the incidental signals can be used to improve the inference stage. Note that we will always assume that we have a small scale of code annotations and a large scale of incidental signals. Given various types of incidental signals, what can we expect? We can at least expect that incidental signals should be helpful for code annotations. But can we determine ahead of time the relative benefits of partial data, noisy data, and constraints? Yes, we can do that with the help of PABI. We see that there's a strong correlation between the relative improvement in experiments and the PABI computed ahead of training for various types of incidental signals, including partial labels, noisy labels, auxiliary labels, and some complex types of incidental signals, such as a combination of partial and noisy labels, a combination of partial and constraints. The takeaway here is that the informativeness of a signal can predict the improvement provided by the signal. it's possible for us to compare and predict the potential contribution of incidental supervision of different types with PABI ahead of training. We also evaluate PABI in cross-domain setting. Here, cross-task signals are a special type of incidental signals. We will always assume that we have a small set of main data set and a large scale of cross-domain data sets. In NER, we use Twitter as the main data set and the other 3 large cross-domain data sets. And we in QA, we use Squad as the main data set and 3 other cross-domain data sets. As for model, we use BERT and we use joint training and pre-training to make use of incidental signals. As for informativeness measures, we consider 2 baselines. The first one is vocabulary overlap baseline based on the most frequent unigram overlap. And the second baseline is as follows. We will first train the system on the large scale cross-domain signals and directly evaluate the system on the target domain. The error rate is something like the cross-domain performance serve as a naive baseline and finally PABI. So in our experiments, we found that there's a strong correlation between the relative improvement experiments and the PABI in 3 settings: joint training NER, joint training QA, and pre-training QA. Compared to other 2 baselines, we can see that the correlation between PABI and the relative improvement is much stronger. In what we can see that PABI can be used to measure domain similarity in some sense. Overall speaking, we can see that PABI is a good informative measure for various types of incidental signals. Now we can take a look at the third part, weighted training for cross-task learning. So given a source task such as post-tagging and a target task such as NER, how to use post-tagging to help NER is a standard cross-task learning setting in natural language processing. So usually we will have a large scale of post-tagging and a small scale of NER annotations. In this part, our goal is to provide some efficient algorithms to better use cross-task signals. Why we want to study cross-task signals? First, cross-task signals are widely used in real-world applications. Second, there are a lot of difficulties remain in using cross-task signals. However, for instance, how to measure the similarity between different tasks is unclear. Even in PABI, we found that predicting the benefits of cross-task signals is quite hard. We have to make some simplifications there, and because, for instance, even though we know post-tagging is helpful for NER, but we don't really know the exact relation between 2 tasks. So measuring the task similarity is quite hard in general. Other problem is that we don't really know how to understand the impact of fine-tuning. Currently, the mainstream methods use fine-tuning in experiments, but we don't really know why fine-tuning is beneficial. So, for instance, we at least have 3 ways to learn representations. The first way is to learn representation from scratch in the target data. Try to select some representation in the representation space big file. And the second way is to use source data, large-scale source data to learn the representation file head and directly use the representation in the target task. And the third way is to first learn the representation file head in the source task and then fine-tune the file head in a smaller neighborhood compared to the whole representation space. Try to find a better one for the target task. Intuitively, we can see that fine-tuning should be a better choice in general, but we don't really know why it's beneficial. So before going to our work, we first recap some background in learning to learn. There are 3 spaces in learning to learn. First, feature space X. Second, latent space Z. Third, label space Y. We will have a complex representation model file in a collection of representation maps, big file, mapping from input space to latent space. And we will have a task-specific function F in a collection of task-specific functions, big F, mapping from latent space to feature space. In learning to learn, we will have T source tasks and 1 target task. As for training examples, there are a lot of training examples in source tasks and quite a few training examples in the target task. Usually, we will have a two-stage empirical risk minimization procedure for learning to learn. First step, we will try to learn the representation map from the large-scale source data. After that, we will learn the task-specific function from the target data based on the representation learned from the source data. And the second step can be replaced by a fine-tuning stage. So existing theoretical analysis will always assume there is a shared representation for all tasks. But this assumption can bring us some problems, even though it's quite good for understanding the benefits for use source data. Why? Because you can see if you already assume the shared representation for the all tasks, then pre-training the model on the source data can have a better representation, which is helpful for the target task. This assumption also brings us some problems. For instance, it makes the situation harder to measure the task similarity because we already assume the same representation for all tasks. Then we can only use task-specific functions to measure the task similarity. However, task-specific functions are not expressive enough and are quite simple in general. Another problem is from the fine-tuning. If we also already assume that the same representation for all tasks, then there's no need for fine-tuning. Therefore, we relax this assumption by allowing that different tasks can have different representations. In this way, we can use the similarity between representations to measure the task similarity. And we can try to measure the distance between representations learned from source data and representations learned from target data to understand the impact of fine-tuning. Formally, we propose representation-based task distance. The representation-based task distance between W-weighted source tasks and target tasks is defined as following. Here, weights are on tasks, but we can easily turn to cases where weights are on examples. Big phi W are optimal source representations, and phi 0 star is one of the optimal target representation. We can see that the task distance is based on the worst target population risk for representation in the optimal source representations. For instance, if optimal source representations are a subset of optimal target representations, then the task distance is 0. If optimal source representations are quite different from optimal target representations, then the task distance is large. To better understand the task distance, we consider a small experiment here. We use 10K training examples for the source task and consider two learning paradigms. Single task learning means learning only with the target data. In learning to learn, we first learn the representations in the source data and then learn the task-specific function in the target. So now let's look at the results. The x-axis will be the size of target task. So we can first look at the single task learning, the black line, as a baseline. So for now, we can take a look at the learning to learn with free period 0.0. Here, free period is an important factor in generating the source data. And the lower free period indicates smaller task distance between the source and target data. So we can see that if we consider learning to learn with free period 0.0, it means that the source data is quite similar to the target data. In this way, learning to learn is always better than single task learning. And another extreme case is learning to learn with free period 1.0. In this case, source data is quite different from the target data. Then learning to learn can be always worse than the single task learning. And in general, we are in middle cases. For instance, for learning to learn with free period 0.4, the shadow blue line, we can see that if we have quite a few target training examples, then learning to learn is better than single task learning. But if we have large scale target data, then learning to learn is worse than the single task learning, because the source data can not only bring some information, but can also bring some noise in the middle cases. So it means that task distance plays an important role in the benefits of learning to learn or the benefits of source data. The observation is that smaller task distance between source and the target data indicates better pre-training performance. recap that our goal is to provide efficient algorithms to use for task signals. Here we propose TAWT, target-aware weighted training. We try to find a better weight W on tasks or examples to make the task distance smaller, because smaller task distance means better performance. The specific goals in the pre-training stage will become twofold. First, find the best weight that minimizes the task distance, and then find the best representation that minimizes the training loss. Why this algorithm can work? Now we can take a look at the picture. So for target data, we will have a quality of representations. The x-axis will be representations and the y-axis will be quality. If we don't have any source data, then the quality of representations will be uniform because we don't know which representation is better. But if for source data 1 and source data 2, we also have relevant distributions for quality of representations. We can see that target data is more similar to source data 2 based on the quality of representations. In this way, actually, we should, if we pre-train the model on both source data 1 and source data 2, an intuition is that we should assign more weights on source data 2, because source data 2 is more similar to the target data. So if we highlight source data 2 in the pre-training, then the task distance is smaller and the performance should be better. Specifically, for TAWT target-aware weighted training, we will first initialize parameters such as weights, representations, and task-specific functions in both source data and target data. For each iteration, we will first freeze weights, and then we can run several SGD based on the source empirical losses to update the representation and the task-specific function in the source data. After that, we can freeze the source model, try to run SGD based on the empirical target loss to update the task-specific function in the target task. In this way, we can see that freeze weights, we can update the model. After that, we can freeze the model to update the weights based on merit descent. Here we use merit descent because weights are a probability distribution and the merit descent is a more suitable choice. The key is the gradients of empirical target loss with regard to the gradients of weights with regard to the empirical target loss. There are three terms. The first term is the gradients of representations with regard to the empirical target loss. And the third term is the gradient of representations with regard to the empirical loss for source task T. And the second term is the inverse of Hessian. Usually the second term can be approximated by some simple one. For instance, in model agnostic meta learning, they approximate the second term with a constant multiply an identity matrix. So the key is the first term and the second term. We can see that the key for the gradient is the inner product between two gradients over representations. And this inner product between target task and the source task T can indicate some similarity between source task T and the target. In this way, we know that we can update the weights based on the model, and we will have an iterative algorithm between weights and the model. Formally, we actually have theoretical guarantees for TAWT. That F0 had be obtained via TAWT under some reasonable assumptions. We can bound the population risk for the target task for the estimator. There are three terms. First term indicates the error of learning the task-specific function in the target task. This one is unavoidable because every model definitely needs to learn the task-specific function in the target task. And the second term is the error of learning the imperfect representation from the source datasets and then transfer the knowledge to the target task. So note that we will always assume that we have a large scale of source data compared to the target data. So n will be much larger than n0. So second term can be ignored in some sense. And the third term is the task distance. We can see that if we have a better estimation of weights, then we can have a smaller task distance, and then we will have a better transition performance. So we also evaluate the TAWT in experiments. We consider 4 structural prediction tasks in NLP, such as pulse tagging, chunking, predicate detection, and NER. And we consider 3 learning paradigms: pre-training, joint training, and normalized joint training. So joint training here we will assign the same weights on every example. But for normalized journey training, we will assign the same weights on each task. Then it means that the examples from the task with larger data sets will have smaller weights because the overall weights on each task is the same. We can see that in our setting, we will have one target task and the remaining 3 tasks are source tasks. And we will have a large scale source data, 9K, and a small set of training set of target tasks. In this way, we can see that TAWT can improve 3 learning paradigms on 4 tasks. And the results indicate that TAWT is an efficient algorithm to use cross-task signals. As a byproduct, we found that normalized joint training is better than widely used joint training in balanced settings, because we will have large-scale source data and small-scale target task here, so the settings are imbalanced. Finally, we can first recap what we done now. For the key is for incidental supervision is use existing chip signals to help target tasks. In quiz, we try to export information from some chip signals, namely QA signals, to help various tasks. And in PABI, for given target task, we try to select signals from a wide range of incidental signals. And in TAWT, we try to design efficient algorithms with both theoretical guarantees and empirical evidence to make use of specific types of incidental signals. In addition, we also consider incidental supervision in other settings. For instance, early stopping partial annotation. In early stopping partial annotation, we try to use partial signals in structural learning. And in spatial BERT, we try to use cross-modal signals to help spatial relation. And in QA-MR, we try to use QA signals for nominal semantic reliability. So as we can see, our previous exploration mainly focuses on the aspect of incidental supervision. In future, we plan to further explore in this direction by taking into more account properties of natural language. Specifically, we want to have a better understanding on the benefits of the structure and want to work on reasoning in natural language. So as we all know, most NLU tasks are structured. For instance, in the figure A, given a sentence, I met with him before leaving for Paris on Thursday. If we know that met is before leaving and leaving is included by Thursday, then met can only be before or be included by Thursday. Met cannot after the Thursday, right? So we also have similar structures in syntactic opacity, in semantic reliability, and lambda anti-regulation. On the other hand, we also know that structure is beneficial because we have a lot of frameworks to use structure in NLU tasks, such as conditional random field, interlinear programming, and post-real recognition. But actually, we don't have an exact understanding why these structures are beneficial in theory. So the intuition is that if we have tighter structure in the task, then we will have a simpler task, and which means more benefits with the structure. However, existing theoretical analysis has a contradictory discovery, where stronger dependency among paths would lead to worse transition bounds. Why? For instance, you have m examples, and for every example, you have n tokens. If you have quite strong dependency in the sentence, then the effect sample size is m. If you have quite a loose dependency in the tokens, then the effect sample size will be m times n, right? So it means that stronger structure will lead to few examples, effective examples, but they didn't have a clear understanding on the problem itself. Why? Because stronger dependency will also lead to simpler problem because the concept class can be simpler or in some sense. So we need to understand the trade-off between the effective examples and the task complexity that can be influenced by the structure. So you know what? Structure is very important, and we should try to use structure to elevate the supervision bottleneck. Another direction is about reasoning in natural language. Among 125 important questions collected by science for its anniversary. There's one question quite relevant to us. What are the limits of learning by machines? Computers can already beat the world's best chess players, but abstract reasoning is still beyond any machine. Although we have a wealth of information on the web. For instance, in the neural module levels for reasoning over text paper, there's a question who killed the longest field goal in the second quarter. We can actually pass the question into smaller actions, and for each action, we can execute on the long paragraph. So we can see that if we simplify the complex question into smaller one, then the problem can be simplified. In a word, we should have a better understanding on reasoning so that we can simplify the model and then reduce the demand for large-scale data. For instance, given the question, did Aristotle use a laptop? If we directly search the question in the web, we may find the book Aristotle's laptop. But actually, we need to decompose the question into smaller one. For instance, when did Aristotle die? When was the laptop invented? And what happened first? This is a quite hard problem because we first need to determine the perspective for the question. There are many perspectives such as time, location. As long as there's one perspective that we can find some contradiction for the question, then the answer should be no. But even though we know this question is relevant to the time perspective, we also need to determine the operation. So the operation is the third sub-question, who happened first. Here, this operation is time comparison, but we can actually have other types of operations. Therefore, it's quite hard for us to supervise these sparse events because we cannot learn everything from scratch. We definitely need to decompose the tasks into smaller ones. As we all know, our AI systems are not doing reasoning and fail miserably when facing new situations. We definitely need some reasoning formulations to guide us. This is a lot of a new problem. We already have a lot of theoretical formulations for adaptive reasoning, deductive reasoning, and others. Among them, learning to learn showed the advantages of joint learning and reasoning in a formal way. This is relevant to current mainstream model, the end-to-end deep networks, which also assumes that we shouldn't predefine the reputation ahead of time. But we also need to decompose the problem into smaller one and then compose the solutions back. For instance, for last Mitchell, given the picture, we actually need to first identify some units. For instance, for the ice water picture, we can propose many candidates, such as ice, stick, water, bottle, and for every component unit, we have multiple proposed candidates. And finally, we have a lot of combinations for the problem. And we need to determine the best global interpretation among various combinations of small components. The key here is that we should assign values to multiple variables, and there are some dependencies among these variables. This is also relevant to the incidental supervision because we cannot directly learn this task from scratch. We need to decompose this one into smaller one to elevate the supervision bottleneck. As a summary, we want to work on natural language understanding, but there are a lot of difficulties such as variability, ambiguity, hierarchy, and perspectives. To supervise these complex tasks, we should use incidental supervision instead of supervised learning. And our contribution so far is as following. First, we try to explore information from cheap signals to help various tasks. Second, given a specific target task, we want to select appropriate incidental signals among a wide range of signals. Third, we want to design efficient algorithms with both theoretical guarantees and empirical evidence to exploit specific types of incidental signals. As for future work, we want to have a better understanding on the benefits of the structure and the reasoning in natural language by providing motivating examples and design better, more suitable reasoning formulations. Okay, that's it. Thank you. Any questions?
Yeah, thanks, Hangfeng, for the very inspiring talk. And I do have a couple of questions, but I want to see if the audience have questions. supervise. Yeah. Yeah, I guess anyway, I can start with my question because maybe the audience will use some time to type in their questions. So, one question I've been had for quite some time is, I think right at here you use this term called incidental supervision, but I do think in quite some other scenario we will use another term called indirect supervision. So I wonder if you can explain what's your opinion on the difference between these two.
Okay, yeah. Actually, I think incidental supervision and indirect supervision are quite similar in some sense. But the indirect supervision, formally they are proposed for some specific tasks, such as you can extract some entity relation with indirect supervision. They are previously mentioned in some specific settings, and the incidental supervision, something like more general to highlight the supervisions from some chip signals. And actually, there's another difference between incidental supervision and transfer learning. So they are kind of relevant. Incidental supervision highlights that we should use signals, chip signals is from the signal perspective. And transfer learning is from learning paradigm or learning algorithm is from model perspective. So that's the relevance.
So
that's the question.
Yeah, so do you think if we can say something like incidental supervision is a part of, indirect supervision is a part of incidental supervision? Because my understanding is that in incidental supervision, in addition to things which looks like indirect supervision, there are also, as you said, modeling of the label, structure of the label space, plus learning from feedback from users, something like that.
Yes, you're right. Yeah, but that's my understanding. But people may have different opinions.
Yeah. Another question I had is that definitely I agree that lots of the prediction tasks are structural, so definitely it's always beneficial to study any kind of latent or explicit structure in the label space. But at the same time, if we are thinking about just having a better way to represent the, for example, meaning of the labels, does it have to be structural? For example, what if we can consider as a kind of knowledge which is not structural, for example, definitions or gloss knowledge of labels? Those can still help you, jumpstart the label representation if they are few short or zero short, and help the model understand the meaning of the labels, but it's not necessarily being structural.
Yes, definitely. Yeah. Actually, we will build structure as a specific incidental signals. And the meaning of a label space is also a type of incidental signals in some sense. For example, the Wikipedia definition or definition dictionary.
I see.
Usually, we always involve structure because NLP tasks are most structured. That's why. But definitely there are two type of information.
Yeah. Yeah. Okay. Just to mention, recently, my group had a collaboration with Wenpeng. We just submitted a paper to TACO that's about using indirect supervision from natural language inference for ultra-fine entity typing. But I may discuss with you later about whether that should be incidental supervision or indirect supervision as we have used in that paper. But anyway, we can talk about that during the one-on-one meeting we're going to have. Yeah.
Okay.
Yeah. So any other questions from the audience? Yeah, I guess, well, Hangfeng, okay, I don't think you have that in your slide. So yeah, I see someone's posting in the, yeah. Okay, there's one question by Chan Yuchun, hope I pronounce your name correctly. So the question would be the difference between can you explain the difference between the incidental supervision and also weak supervision? Oh yeah, that's a great question. I also wondered as well.
Actually, in my view, I think it's those will include the weak supervision, but if we don't need the so fine-grained distinguish. We think I can think incidental supervision is quite relevant to weak supervision or indirect supervision. They are quite similar, but they definitely have different highlight. For example, incidental means that highlight that signals are there already, and you don't need to make extra efforts to annotate it. So they have different highlight and have different scope, but they are quite a fine grained difference. In general, we can see that they are quite similar.
Yeah. Yeah, feels like now incidental supervision, this concept is still quite broad, so we probably need to find a way to actually narrow down and clearly tell the difference from this, and also, you know, the other things I've mentioned, like indirect supervision and also weak or distant supervision. Yeah.
Yes.
Yeah.
Right. Yeah, these are terminology problems. Oh, there's another question.
Okay, yeah, another question from Ashton. So it seems that PABI is limited to classification tasks. Have you thought about extending it to embedding space to be able to use for other tasks, for example, generation?
Actually, yes, PABI is mainly designed for classification tasks, but for generation task, if you can well define the concept class, or you definitely need some assumption, right? You cannot say that the output is infinite amount. That's impossible. But as long as you can limit the problem into a well-defined concept, it's also possible to directly apply PABI, because PABI is based on the prior and the post layer, which has quite flexible assumption on the concept class itself. So you can have quite a complex concept class. It doesn't matter, but I cannot expect how it can work, because for generation task, a big issue is that we don't really have the good estimation method or evaluation metrics. So,
yeah, I do agree.
Yes, so that's why we didn't choose generation problem.
Yeah, so my understanding is that once classification task, is easy to measure the distance between the label and the estimation of the model, plus also, you know, the estimation in task A versus, you know, the label in task B, that sort of things, versus in generation task, you have to come up with a similar measurement between the distance from the task model and also the ground truth, so as to induce the way to measure the distance between signals in different tasks, right? Something
Yes,
like that.
you're right. So ideally, PABI can be applied too, but because of the issues of generation itself, the situation can be quite complex, and we cannot predict the ability of PABI. Yeah.
Oh, cool. Yeah, this is something we should think about. So any other, yeah, okay. There's another question. I wonder if this could be compared to the use of weak learners in boosting when learning classification tasks, or is it an oversimplification?
I didn't really understand oversimplification. The word.
I guess, you know, can we? Yeah, probably I can.
I understand the first part.
So I guess I can unmute and see, and you know, if you want to ask the question by yourself.
Yes.
Hi.
Hi.
I don't know how you hear me, but anyway, of course, this is far before these deep neural networks, but these weak learners just, how to say, maybe somebody else can help here, but they are very simple classifiers, which just don't really learn the right thing, but they can still be useful for like in the ensemble way to make the right decisions in the classifier when you have a lot of those weak classifiers. So in a similar way here, you have signals coming from or partial signals coming from different other tasks, and then you can get some kind of combined information from them. Do you see something like this as a
Yes, actually, I think usually the use of weak learners in boosting, we will have some unlabeled text in some sense. For example, in call training, so we will also have some unlabeled signals. I think the benefits might be from the unlabeled signals itself, because we can actually view the information from unlabeled signals from different perspectives, and that's why weak signals can help in some sense. So I think weak learners are definitely belong to the incidental supervision, but actually I don't really understand your second question. Is it an oversimplification? What does that mean? Sorry.
I mean, in terms of paradigms or this kind of framework, so you can ignore that. Okay, thanks.
Okay.
Yeah, I guess the ensemble and also the incidental supervision is kind of also going to each other, because really I think at here Hangfeng, you're still talking about very strong learners, right? Versus ensemble is actually ensembling there's an ensemble of multiple weak learners in either the situation where the learner is not strong enough to fit the data, or the task itself do not come up with enough supervision signal, but you cannot look at any indirect supervision or incidental supervision signals from outside of this task. So I do think that these lines of research are probably also going to each other. That's what I feel. Yeah, but I guess we are about reaching the end of the seminar. So yeah, thanks Hangfeng for this very inspiring talk, and also thanks for us to joining this talk, and feel free to reach out to Hangfeng by email if you have other questions. Yeah. Great. Thanks.